Okay, everyone. So today we will cover the second part of reward maximization. I don't know how many of you guys had a chance to look at the slides of the previous lecture. Uh, um, so in the previous lecture, we covered how to define a policy using a language model, how to define a reward model using a language model, and how to train that language model. Specifically we saw that Bradley-Terry formulation for training it's the reward model. Sorry. Okay. So now we have a reward model. We know how to train a reward model. What is the next step? The next step is how to train the policy using the reward model, and that's what today's slides are going to be about. How to train the policy. Okay. Um, okay. So we defined the problem of training the policy as regularized reward maximization. Uh, so what does that mean? You want a policy whose outputs on an average have high reward, right? So that is a reward maximization problem. So how do you write that? If you have to write that, okay, I want a policy whose outputs, whose sample, if I generate outputs from that, they have on an average high reward. What does that mean? In mathematically, what does that mean? Any idea? Does anybody remember what does that mean? So your policy is pi theta, and if I sample an output from that pi theta, the reward of that output on an average should be high. This is what it means to maximize the reward. And we also said that we don't want the policy to deviate too much from the starting point, the base policy, also called the reference policy, right? And how do we achieve that? We minimize the KL divergence with respect with that policy. So the second term is the KL divergence between the policy and the reference policy. And we said we can also write this as expected value under the policy, this quantity, log of the probability that policy assigns over the probability that pi ref the base policy assigns. So this the first term we want to maximize the reward. The second term we want to minimize. So when you do regularized reward maximization, you combine both the terms by adding a beta factor so that you can control how much you want to maximize the reward versus how much you want to minimize the KL, stay close to the reference policy. So the combined objective can be written as xy minus beta times log. This is what we covered in the last class. Is everybody fine with this formulation? Okay. So this is how it looks, how you will implement. So whenever, as I mentioned earlier also, that whenever you think of expectation, the immediate picture that should come to your mind is sampling. Okay, expectation is almost always done using samples. Nobody computes expectation exactly because it's generally impossible to compute exact expectation. So this is what should come to your mind. So that you have this policy, and you have there's a prompt that goes an input to the policy, and you get a bunch of outputs. These are the y1 to yn that samples from the policy. Then for each of the output that you get, you compute the reward. You compute the KL term. This is the second term you require, the reference model log probability you require for the computing the KL term, and then you combine them by using a beta scaling factor. And finally, you take the average. So everybody should convince themselves that this particular image captures exactly the expression that we saw previously, this last expression. sampling from the policy and then computing the reward and uh, as well as the KL term. Okay. Okay, so we have this objective that we want to optimize. Objective is fine. How do we maximize this objective is what we need to find out. So looking at the figure, can anybody think how do you, like if you have a graph, generally if you have a graph like this, uh, the standard way to optimize this loss, this is the what we want to maximize, right? This is the maximum, we want to maximize the average reward, right? So generally, if you want to maximize some quantity which can written as a graph, what can generally do is that you can basically back propagate this reward all the way to the parameters and train it. There's a, I mean, whenever you have a graph structure, you can always back propagate. But here, there's a problem with back propagation here. Can anybody see why we cannot just maximize the reward by back propagation here? What is preventing me? So see, what generally people will do is that if I call this output as R, I will compute the gradient of this R with respect to this policy parameter. So gradient of R with respect to theta, and then not even, I don't need to compute actually. I can just back propagate R and that will give me the gradient and then update it, right? So let me, the gradient will be computed automatically by back propagation. But here, there is something preventing me from back propagating the gradient all the way till the policy, and that is the sampling step. This is a non-differentiable step. Why? Because you are sampling discrete quantities, which are the poems, right? And it's highly non-differentiable, in fact, because you're not even sampling one discrete token, you are sampling a sequence of discrete tokens. So there's no way for the gradient to flow from here to there. Otherwise, you could have simply done backpropagation and you would have been done with it. So what do you do in that case? If you cannot backpropagate the gradient from here to all the way to the policy, then you have to do something else. Okay. So this is just a note on regularized reward. If you maximize the regularized reward, you ensure that outputs that are generated by the policy have high reward and they have reasonable probability under the reference model. This is just a small note on regularized reward. Okay. I'm using this notation RS for the regularized reward. Okay. So now the question is, how do we maximize? Since we cannot backpropagate the gradient, what we need to do is something which is called the reinforce trick. The reinforce algorithm, and the idea is that you compute the gradient of the objective first of all. So and the objective is your expected value of the regularized reward. So how does the gradient look like? Let's compute that. Just a analytical gradient computation. So first thing is expand this expectation. This you can write this as summation over y belonging to the domain of all possible outputs, pi theta y given x times the regularized reward x comma y. The gradient of this quantity. This is the gradient that we want to compute. Then you can take this gradient inside. This is fixed. This reward function is fixed. Let's assume we have already trained the reward function. Okay, so this can be written as summation over all outputs, gradient of the policy times the reward. Okay, there's nothing interesting about this. So let's see what next. So this is the expression we got. Yeah. Okay. So this is the expression that we got. Now, this exact summation, if we try to compute it, we have to sum it over all possible outputs, which is not possible. So what can we do? So we want to replace it with something that we can approximate. So question is, can we approximate this quantity using samples? This quantity, can we approximate using samples? if I directly take some samples, so forget whatever is written below. If you have to just look, if you just look at the expression, where should these y's come from? I mean, just looking at the expression, it's not telling me where the y should come from. Uh, it is not telling me where to sample these y's, in fact. Okay, so I want to convert this expression to an expectation. So why do I want to convert it to an expectation? So that once there is an expectation, then expectation immediately tells you where the samples should come from, and that's what I want. I want this expression to become an expectation. Okay. So we need an expression of this form: expectation under some distribution. Here it is written the policy, but it can be any distribution. I am fine as long as I get expectation under any distribution, because then I can approximate it using samples. So this is and basically what this means is this is how I want the expression to look like. So that's what we will achieve in the next slide. Does this make sense? The why do, first of all, this does it make sense that why do I want an expression in the form of expectation? So the thing is, if you look at the expression at the top, it tells you that for each output possible, so there are infinitely many sequences possible, right? For each sequence, compute the gradient of the policy times the reward of that sequence. Now this is not possible, so I somehow need to replace this with a few samples, right? And this is, so the question is, where should these samples come from? Okay, when there is an expectation, I immediately know where the sample should come from. It should come from the distribution or, for which you are computing the expectation. But so that's why I want this to become an expectation. Does it make sense? Okay. So we use this trick called the log derivative trick, and it's a not a it's a very small trick which basically says that the gradient of if you have this term log of policy, and somebody asks you what is the gradient, how would you write the gradient of it? 1 by policy. And what does this mean? If I just now I want to bring this to the left hand side, so this quantity can be written as policy times log, or gradient of log. So this is what I'm going to, this quantity is what I'm going to replace in the term that we had. So let me write down what we had earlier. What we had is this quantity. The earlier derivative that we had was summation over y belonging to y, the domain of all outputs, gradient theta pi theta y given x times rs x comma y. And now I want to replace this quantity by this. Okay, so this will become summation y belong to the domain policy times gradient of theta of log of the policy times reward. And now does it start looking like an expectation? Can anybody see if it is an expectation, and if it is, what is the next? How do I write it in as an expectation? What is the distribution for the expectation, and what is the function that whose expectation I'm computing? Yes, policy is the distribution, and the function whose expectation I'm computing is gradient times reward. So, yeah, so let me write the reward first, times gradient. Is this fine with everybody? So this is the log derivative trick. It's a very small trick. There's nothing fancy about it. It's just a small trick, but it allows you to compute the gradient using samples. Because now we have an expectation, and I can replace. So as I mentioned earlier, whenever you think of expectation, think of samples coming from the distribution under which you are computing expectation. So let's look at it. So now this expectation can be computed, right? How would you compute this expectation? This is what you can do is you can take the input, feed it to your policy, get a bunch of outputs, compute the reward of each output, and also compute the gradient of the policy and multiply the reward and the gradient, and then take an average. So this image is just computing the expectation of the gradient times reward. That this image is exactly computing what we had in this expression. So with just looking at the expression, you should imagine what how you should be able to compute it. You the way you think is that this is the policy. I should get the samples and then compute both of these quantities individually and multiply and average them out. That's all, and that's all this figure does. So this is all. This is, I mean, Monte Carlo is a fancy term for whenever an expectation is replaced by samples, then we call it a Monte Carlo approximation. So it's approximation of expectation. Probably Monte Carlo were the first who thought about this approximation of expectation through samples. Okay, so now we know how to compute the gradient. Let's expand the gradient in terms of token. So because see, ultimately you have a language model and your actions are tokens. A sequence, the output that you generate is a sequence of action. It's not an individual action. It's a sequence of actions. And each action is one token. Okay. So what I want to know is that for each action that I have taken, for each token that I have generated, what is the weight that I give to that generated token? How, I mean, do I increase the probability of the generated token? Do I decrease? What is happening at the token level is what I want to know. Okay, so let's expand it in terms of tokens. So let's say y equal to a1 to am, and the reason why I'm using a1 to am is because a are the actions. Actually, I should use a1 to at. So let me make this t. Okay, so this becomes reward times gradient of. Now log of a log probability of a sequence of actions, I can expand this as summation over t equal to 1 to t log probability of a t given st, where st is the input prompt and all the tokens that I have generated so far. And now I can take the summation outside the gradient. I can write this as less x comma y. Thanks. So this becomes summation t equal to 1 to t gradient theta log of phi theta at given st. And let's take this reward also inside. This becomes summation t equal to 1 to t reward times. So basically each token is getting the same reward here. So we'll see the example, but from this expression what it tells you is that the first token, the second token, the third token, all the tokens will get the same reward, and that reward is the reward of the complete output. So even if you have generated only one token, the reward that it will get is the reward that you will get of the complete output that you generate. Okay, this is how it will look like. You'll have a decoder model, a large language model, a policy. You will have your input prompt, and you will have the tokens that your model generates. So let's say this is what is generated by the model. Okay, by generated. So each so the log probability of the token. So this you generate the first token condition on the last condition on the user prompt. So the weight that will be that the first token of will get is the reward of the complete output. Similarly, similarly for each token here, and I have not written gradient here. I just directly written log probability. And when I'm doing reinforce, when I earlier I derived the reinforce as the gradient of the expected log likelihood, but here there is no gradient term here. So can anybody guess why there is no gradient term here? So the idea is that you are multiplying the log probability of each token with the reward and then summing them up, and then you are back propagating. So when you back propagate, these gradients will be computed automatically. So you don't have to explicitly compute the gradient. Backpropagation will automatically do the job of computing gradients, and then you will do the updates. Okay, so basically what this figure says is that you can implement reinforce simply by feeding the input, feeding the output, both generated output both to the large language model you have, and multiplying each token's log probability with the reward, and then summing it up. It's very similar to how you do supervised fine tuning. Like if there was no reward, there was no, this R term was not there, and if I was just doing this is exactly supervised fine tuning, but on the generated outputs. So what reinforce adds is this R, this reward term, that is that extra in reinforce. Does it make sense? So reinforce is supervised fine tuning of generated outputs times the reward of the generated output. So now what is the problem with this? Let's think about it. Let's go back to the old figure and think what is the problem. This token, I generated the token Taj here, and the reward that it gets is R. Now the entire sentence, if you look at Taj Mahal is in Agra, end of text. This sentence is correct, so the reward will probably be positive. But that doesn't mean that Taj, I should increase the probability of Taj, because the output could have been equally Taj Mahal is in Paris. So if the output turns out to be Taj Mahal is in Agra, I am increasing the probability of the word Taj. See, whenever this is positive, that means I'm increasing the probability. Whenever the reward is negative, that means I'm decreasing the probability. So based on the reward of the entire output, I'm deciding whether to increase the probability of Taj or not. So if the model had generated Taj Mahal is in Paris, the reward would be negative, and I would be decreasing the probability of every word, decreasing the probability of the word Taj, decreasing the probability of the word Mahal, every word, because the log probability of each token is getting multiplied by the reward. And if the model had generated Taj Mahal is in Agra, the reward would be positive, and you would be increasing the log probability of every token. And that is problematic, right? Because ultimately the generation of the token does not, the Taj is not highly dependent on the reward. The token, right? Taj is not dictating what the reward will be. So this variance in the reward leads to very unstable training. I don't want the weight that the word Taj get depends on the output of the final sequence, right? Because it might generate an arbitrary lots of sequences, right? And every time this word Taj might get a different reward. So there is huge amount of randomness in the reward that this log probability of the word Taj is getting. So what do? I want to reduce this variance. So think about it. Like you don't want the word Taj, the weight this word Taj gets depend on what gets generated in the future. So what do? Like, yeah, can anybody think? You have so many sequences that are possible from a given token, and you want to somehow remove the dependence of the random sequence that you end up generating, right? You don't want to make the reward dependent on which sequence that you ended up generating. So what do? You basically say, okay, I am already generated Taj. Now what? Assume that I can generate all possible sequence after Taj, okay? And for each of the sequence, I could compute the reward. And that average reward is what the word Taj should get. So the word Taj should not get the reward based on the random sequence that you ended up generating after that, but average over all possible sequences. So that is called the Q function. Does this, yeah. So I will not go in lot of mathematical detail, but some details about what the Q function is. But intuitively, the idea is the Q function is the average cumulative reward you will end up getting if you generate a huge number of sequences after Taj from the policy. So, and because you're averaging, this becomes, I mean, you have to reduce the randomness in the reward that you're giving to the word Taj. So, does it make sense? Right. So, when we do the final expectation, when we do the final expectation, we are computing the average of the gradient, right? Now, but how much weight should this? If you look at the word, this word, right? This is not coming from any average. This is coming from this particular sequence. That whatever reward that this sequence got is the reward here. If this sequence was correct, Taj Mahal is in Agra, so this reward would be positive. If this sequence was incorrect, this reward will be negative. But and what this happen what as a result what happens is that the model sometimes thinks that okay, Taj is the correct thing to do here, and sometimes thinks that the Taj is not the correct thing to do here. But it doesn't matter, right? Taj or no Taj, whether it's the reward, its contribution to the reward is negligible. What matters is the final word, Agra, right? So there should be some mechanism that you can run multiple policies from here, and generate multiple outputs from here, and compute the reward of each output and use that quantity here. So you somehow you want to replace this an average. That's what you want to do. And similarly for all the other rewards, for each of the rewards you want to see, if I continue generating lots of sequences from this point, what will be the average reward that I get, and use that as the reward. So let's say there are 100 possible sequences from this point, okay, and you want to look at all those sequences, compute the reward of all those sequences, and take the average and put it here. For hell, again, you want to look at all possible sequences that can but you will not do it. But that's what you want to do actually. I mean, you will we will not do that. Obviously, that is not possible to do. Like generating all possible sequences at every point is kind of impossible, right? You'll have 100 times, 100 times, 100 times, like 100 to the power number of tokens that are there. Like that is impossible to handle. So what can we do? So first of all, we should convince ourselves that this is a good idea. Replacing random reward is actually bad for training, and you should replace it with something that is more stable. So what I have done here is that instead of the reward, I have replaced it with the Q function. So earlier there was a reward, and this Q function is an average of all average reward over all possible or all likely sequences. Let's start with Taj. Start with Taj. So what I mean likely is that this Q is actually a function of the policy. I'm not written the subscript policy here for simplicity, but this Q depends on your current status of the policy. So you will run the policy at this from Taj, generate multiple sequence, take the average reward, and put it here. Okay, so what this has removed all the randomness that was there in the reward for Taj. Now the reward at the token Taj is fixed. And that is the Q function. Does this make sense? Okay. Yeah, so the Q function is, as I mentioned, is the average discounted. There is another thing in RL called discount factor, which basically says that you do for the current token, not all the tokens. If you're computing the weight for the current token, the tokens that are closer to this token should have higher weight compared to the tokens that are further. Like the reward that the nearer tokens receive should be given higher weight than the reward that the future tokens will receive. Okay. So the Q function of state action pair is the average. You basically generate bunch of outputs. 80 plus 1, 80. You generate a sequence, bunch of sequences. 8. Given the state, and then compute the reward of the entire sequence. And this is called the discount factor. So what this discount factor is actually close to 1. It's somewhere around 0.9 or 0.95 or whatever. And what this discount factor does is that it says that when I am computing the Q function for at T for the token T, then I need to look at tokens, the rewards that I get in the immediate future. Those are more important, and the reward that I get later on, those are less important, because and this idea originates in reinforcement learning in games. So when you are playing games, the step that you take right now will have more likely to impact immediately, and the later impacts that it will have you don't know whether it is because of this particular action you took or some other action that you took in the future. So this discount factor actually originates from games, use of reinforcement learning in games. So that's the Q function. The value function, so Q function is defined for a state action pair, that if this in this particular state I took this action, what is the average discounted cumulative reward that I will receive, right? And the value function is defined only for a state. The value function is basically if given that I have reached this state, what if I continue running my policy, what is the average discounted reward that I will end up receiving? So Q function is the only difference between Q and value is that Q function depends on the action that you took at a particular state, and value function depends only on the state, that okay, I have now that I have reached this state, now that I've reached this state, if I keep running my policy, so 80 plus 1 plus t, how what is the average reward that I will end up getting? Yes. But so even if you don't let's say don't understand this expression, okay, by the way, this st plus 1, where does this st plus 1 come from? So st plus 1 is, in the case of language model, st plus 1 is simply the previous state and you append your token. So st plus 1 is just when you append your token 80 to the previous state. Yeah, yeah, it will get squared actually. Let me gamma square, let me put this gamma square so that you get that is squaring. Yes. Okay, so even if you don't like this expression, mathematical expression, because generally these expressions originate in when you do a proper reinforcement learning course, but these are just few classes for covering PPO, so you can get an intuitive picture of what this Q and value function is. It's just the average reward from a particular state or from a particular state action pair. Is that fine? So as I mentioned, we are dealing with language models, and the next state is completely determined by the action that you take at that state. Okay, so st plus 1 is st appended by 80. So the Q function for the Q function can be written here as in this form. The Q function for state and an action pair is equal to the reward of that state and action pair plus discount factor times the value function of the next state. So this is the next state, and you can derive this from the equations that we wrote here, but for now you can just take it for granted that this is true. Okay, so so to further reduce, so actually I mentioned earlier, right, that the Q function is used because you don't want a lot of randomness in the reward that this token receives, right? Now to further reduce variance, and what is generally done, that you subtract the value function from the Q function to get the advantage function, and that's what you use during training. And proof that this actually reduces variance is not included here, but for now the way you can think is that the smaller numbers you multiply with a gradient, the lower the variance is going to be. So these Q values can be actually pretty high, and value function removes the contribution. So basically what you want is the contribution of this specific action AT at time t, right? And so value function removes the average contribution of any action, so that you can have taken at that particular point. So it's a sort of an average over all actions at st. So by subtracting the value function, you are saying that okay, given that I have reached st, if I take an average action, what is the average reward, what is the reward that I will end up getting, compared to if I take action AT, what is the cumulative reward I will end up getting. So you subtract this quantity, and that's called the advantage function. So this is ultimately how your reinforced with advantage functions looks like. So initially we had reward, that was getting multiplied by the log probability of the tokens. Then we had the Q function that was getting multiplied, and now finally we have the advantage function times the log probability of the tokens. So how? Okay, so in the previous slide I showed that the advantage function can be computed only from the value function. So all you need is to know that given that I am at a particular state, what is the value of that state. If you know the value, you can compute the advantage as follows: the reward plus the value of the next state times discount factor minus value of the current state. Right. So how do you implement this value function? So just like we had the reward function, the value function can be implemented by adding a linear layer on top of a decoder model. You take a decoder model, and decoder model at every step it gives you a probability over distribution over the next token, right? So you add another linear layer. So this gives this already exists in a decoder, exists already, and this is what you are newly adding to your decoder, a linear layer which takes the embedding of the last token and outputs a scalar quantity, a number that is your value. So implementation wise, that's all you have to do: add a linear layer on top of an existing decoder, and you have to do it for each token. So I mean, that same linear layer will act on at each token. Does this make sense? Okay, so how do you learn the value function? You have an input x, you sample an output y, which is a sequence of token a0 to at from the policy, and so okay. Before that, if you think about how to learn this value function, value function is basically the average reward you will get if you keep running the policy from at that point, right? So what you do is you run a policy, get a sample, and compute the cumulative discounted reward at each time step. So RT is basically the reward that you will receive at that particular time step plus discount factor times the reward for the next time step plus gamma square reward of the next, so on and so forth. So this, you do it for each token. At each token you can compute what the future reward is. This is also known as the reward to go. And now you simply train. You know that value function is a neural network. That's what we saw here. This is the value function. So you just minimize the least squares between your VST minus RT whole square, and this you do over all the tokens, and that's how you learn the value function. Let me put a phi over here so that we know that y function is parameterized by phi. And you do it over an entire batch, and that will give you the value function. So this gives you the vanilla policy gradient. What you will do is you will mix the value function training and your policy, the reinforced algorithm, and you will interleave those two. Okay, so you will repeat this until convergence. You will sample a batch of prompts. For each prompt, you will generate one or more outputs, and for each output, you will compute the reward at each token, compute the cumulative discounted reward for each token, and then compute the value and advantage function for each token. So these three things you have to compute for each token, and then you will apply few gradient updates using the reinforced algorithm with the advantage values that you got, and then you will apply few gradient updates to train the value function that we by minimizing the mean squared error. And this you need to keep on doing until convergence. Now the issue is that this requires, so if you look at the algorithm, for each prompt you have to sample outputs and then train, sample and then train. So it requires every time you want to do a gradient update, you have to generate new outputs. So, and that's a bit problematic. You don't want to continue sampling outputs from the policy during training, because that slows down training a lot. and also it makes training a bit difficult because every time your samples are coming from a different distribution, right? So your loss function doesn't because you're doing a stochastic gradient descent, the algorithm doesn't know where there's no fixed distribution where the samples come from, so the training gets a bit unstable. So somehow you want to fix a distribution, sample the outputs, get the outputs, and then run the algorithm. So how do I do this? So let's go back to our starting point when we derived the reinforce. Our objective was expectation under the policy pi theta times reward, right? But I'm saying that I don't want to sample from pi theta again and again and again. Can I fix the policy at some time step and do some updates of training and not use these samples from pi theta every time? So I can write, so it's this expectation as follows: summation over y belonging to y policy times reward, right? Now what I want to do here is I want to get an expectation. The final expression that I want is get an expectation with respect to a different policy, a policy of a previous time step. So how do I get expectation under different policy? What I will do is I will multiply and divide by a previous policy here. So what I will do is multiply with the previous policy, let's say theta k, and divide by the same quantity. And what does this give me? Now what I can do is I will bring this quantity here. So this will give me pi theta k x times pi theta y given x times the reward. And if I have to write it as an expectation, this will become expectation under pi theta k pi theta times reward. So I took an expectation under the current policy pi theta and I replaced it by an expectation under the previous policy of previous time step. And why did I do that? So that I can get samples from, I don't need to continue sampling from the policy. I can get samples from a fixed policy and then do the training. And this term that we get here, this is known as the importance weight. Okay. So this is how reinforced with importance weights look like. Okay. Before that, as a practice at home, you can try computing this quantity, gradient of the objective that we got here. What is it? Expectation under y coming from pi theta k y given x. And again, when you do this, again, in order to convert this gradient to an expectation, you will have to apply the log derivative trick. Okay, so let me write the apply log derivative trick. And I will write down the final expression because that's what I am that's in the next figure. But you can derive it at home. This will look something like this: y coming from y given x okay. So here I assumed reward rs, but instead you can use the advantage function. So wherever there is a reward is written, you can replace that by the advantage function also. And if you have to implement this expression, the way you will implement is this way. You will have an input, you will have the output tokens, and you will feed the generated tokens as well as the input to both policies: the fixed policy, this is fixed, and the trainable policy, this is trainable. and you will get the importance weights, multiply them with the advantage. You can, I mean, although I wrote reward earlier, you can use the advantage wherever the reward is written, and you can sum up those quantities and backpropagate. So this is your reinforcement, reinforce with importance weights. Now PPO does one extra thing, which is a very small thing. What it does is that it says that if you look at this, these fractions that are there, right? These quantities, pi theta by pi theta k. If you keep on training pi theta, these fractions may become very big. So what might happen is that during training, these fractions pi theta by pi theta k may dominate your training, and they may make your training unstable. So what PPO does, it bounds this fraction. It says, okay, the pi theta by pi theta k ratio should be within this range of 1 minus epsilon and 1 plus epsilon during whenever I do an update. Okay, so the way it ensures that these ratios are bounded is that when advantage is positive, it maximizes this quantity, this quantity. This is what is getting maximized, and when advantage is negative, this is the quantity that gets maximized. So we will see why, how that makes a difference. Okay. So let's look at when we have positive advantage. Advantage is positive. Okay. So when advantage is positive, what this means is, if you are maximizing, let's say, so when advantage is positive, that means this quantity will increase, right? So initially, okay, this should be k. Initially, this ratio is 1. The importance weight is 1. Pi theta of AT given ST over pi theta k of AT given ST. At the beginning of training, this is quantity is equal to 1, because you initialize theta with theta k. And now, because at this quantity is positive, this entire expression will increase, right? This one is, and which is less than 1 is less than 1 plus epsilon. So initially, this is just maximized over theta, pi theta over pi theta k times advantage. But as you train theta, this quantity will become slowly bigger. This quantity will keep on growing, because pi theta will keep growing far away from pi theta k, and there will come a time when it will become greater than 1 plus epsilon. And as soon as that happens, the training will stop, because if this quantity becomes greater than 1 plus epsilon, then the min will become equal to 1 plus epsilon times advantage, and there is no parameters here. So this basically, your objective will become a constant. So as soon as your policy deviates too much from the current policy, the model will stop training. Okay. Similarly, for negative advantage, you can derive for negative advantage in the same way, that the negative advantage is negative. So this also key. So what will happen is that this initially pi theta will keep on decreasing with respect to pi theta k, but as soon as it goes with less than 1 minus epsilon, below your training will stop. Okay. So this is the PPO clip algorithm. It's exactly the same as the reinforced algorithm. The only difference is that instead of gradient updates using reinforce, we do the gradient updates using PPO clip now. That's it. The algorithm is the algorithm wise, there is no difference. You sample a batch of prompts, sample and sample outputs, compute the reward, compute the advantage, and then apply few gradients of PPO clip with the advantage values. Okay, so I know this was a very mathematical class. Too much of mathematics was there, and there were too many things to remember. But key factors to remember was, one of the key factor was the log derivative trick to derive the gradient, and the reason why we needed the log derivative trick. Then we replaced the reward of the total reward by the advantage function, so that we can reduce variance that the reward at the intermediate tokens receive. And finally, we used importance weights so that we can sample from a fixed policy rather than keep sampling from updated policy. So in PPO, what is done is that you sample from fixed policy and then do some updates of PPO and then update the fixed policy again. So it's not like you will always fix the policy. The fixed policy will also keep getting updated from time to time. And finally, PPO does this clipping of importance weights to prevent large gradient updates.